Let us begin our today's session with follow-up session, because only going to the videos and saying that we are studying has no importance. So I'm with the one question: are you studying and are you understanding the chemistry that we are discussing in semester 6? Reply there, unmute and talk.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, then let me know
Yes,
your
sir.
study by asking a question. Means that will be the follow-up session. Let us know what you did. Actually, unit number 1 was related to coordination compounds. Two theories are there in that unit. One is VBT, but VBT, considering your study at SY, only limitations are there in that unit, and other is CFT, right from the basis of CFT to the applications of CFT and demerits of CFT. All things are covered in that unit number 1. About limitation, I had asked a question last time. 3 students have attempted. Good attempt they did, but confidence was not more as I was expecting. So let us begin our study with that point. I want the answer from you. Limitations of VBT. Yes, what's the first limitation?
It does not explain transition metals are colored.
It could not explain the color property of coordination compounds of transition series element. Of course, whatever we are discussing, these theories are not for elements. We are discussing this theory for compounds. So coordination compound is one important point to be added there, but it's good. Color we could not explain, spectra we could not explain, electronic transition we could not explain, because VBT has not considered any kind of gap. So excitation and all, how could be possible? Yes, good. Second limitation.
It fails to explain geometrics like tetragonal and octahedral.
Okay, could not explain geometry. Geometry explanation was not the purpose of this theory. Actually, theory is to explain the compound. That's a coordination compounds. Where is the fidelity? It has said sp3d2 or d2sp3 means that there will be the octahedral complexes. dsp2 means square planar complexes. sp3 means tetrahedral complexes. Hybridization was the base of the VBT, and with the help of hybridization, it is explained. But still, point is right. But I want explanation.
It fails to explain reaction rate and mechanism of reaction of coordination compounds.
Okay, it is right. It is next point. I'm coming. Now let me cover about the second point about the geometries. Point was there. Explain that point. See, octahedral geometry means D2sp3 and sp3d2. It is an inner orbital complex and the outer orbital complex. That was the explanation by VBT. But why it is an inner orbital complex? Why it is outer orbital complex? Other than the strength of the ligand, generally strength of the ligand, VBT could not give satisfactory answer about the inner and outer orbital complexes. Means octahedral complexes are not properly explained. Are you following what I am saying?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Now tell me the third limitation. I think Alia was saying. What is the third limitation?
It fails to explain reaction rate and mechanism of reaction of coordination compounds.
Yes, rate or speed of the reaction or mechanism for that reaction, whether it is SN1 or SN2 or SN1CB. You will come to know, you are studying that point. Stability, instability or less stability, magnetic property, geometry, these were the only applied areas. About the rate of the reaction, the mechanism of the reaction, no explanation. So it is a limitation of the VBT. It's good. It's a proper point. Yes, next.
It cannot to make any quantitative interpretation of stability of complexes.
Okay, wordings were not proper, but point is it could not explain stability. It could not use satisfactory interpretation, satisfactory explanation for stability of the complexes. Its explanation was there. It was saying inner orbital complexes are more stable and outer orbital complexes are relatively less stable. It's a qualitative, a general explanation, particularly how much stability is there regarding that. VBT was with no explanation. Proper point. Good. Now, Fifth limitation.
It cannot account for temperature-dependent paramagnetism of some complexes.
Yes, magnetic property it has explained to some extent, means two unpaired electrons are there, then magnetic moment will be 2.43 or nearby them. So magnetic properties are explained to some extent. Spin only formula was used. But for the same complex, if we change the temperature, magnetic moment was found to be different. So what is the effect of temperature on magnetic moment? No idea, because base was not related to the splitting. Base was related to only the hybridization, formation of the complex. If that VBT would have been the true, then change in the magnetic moment would have not been observed if temperature changes. So change in temperature, or with change in temperature, change in magnetic moment was not explained. That was a limitation. Yes. Further.
This theory did not give a perfect bond angle of molecules like H2O, CO2,
Oh,
and ammonia.
okay, see, valence bond theory, of course, you are right, but we are talking about the VBT, which is applied to coordination compounds. The CO2 or H2O, these are not the coordination compounds. With help of that, we can form coordination compound, but those are not the coordination compounds, those are covalent compounds. So our point of approach to discuss the limitation of VBT for coordination compounds.
VBT fails to explain the reaction rates and mechanism of reaction in coordination compounds.
Yes, see here, point number three. Point number three is the same. Rate of the reaction and mechanism not explained. I want new point. Last point say consider.
Idea about quantitative stabilities and bond energies is not clear.
Yeah. See, the stability of the complexes. And of course, it is related to bond energies, binding energies, or bonding energies, stability energies. So, point number four covered.
It fails to explain change in magnetic moment with change in temperature.
Point number five magnetic moment or magnetic properties were found to change with change in temperature. It could not explain. Almost
Failed to explain in some complexes electrons are paired and they remain unpaired.
electrons are paired and they remain unpaired. No, I'm not getting what exactly you are saying. No, it's in some complexes are paired, but they remain unpaired. No, I'm not getting. Is this statement any book?
Yes, sir.
What they said? Read that statement.
It explained it fails to explain why in some complexes electrons are paired and in some they remain unpaired.
Okay, it is why in some complexes, while previously what you were saying in the complex, same complex, actually some or same, it remain the confusion, means electrons are paired, but they remain unpaired. Means but they remain unpaired. But word made a lot of difference. Their wording was few complexes are chromium, few complexes of iron, few complexes of one particular metal ion in which electrons are paired. Means it is low spin. And few complexes electrons are not paired or less paired, means it is high spin. While low spin and high spin complexes are there, satisfactory explanation is not given. Yes, is it clear how wording? What was the wording previously when I said objection? It failed
Yes,
to
sir.
yeah, means electrons remain paired, but they are unpaired. It could not explain. Means in wording itself, problem was there. But word made a lot of what was actually in few complexes electrons are paired and few are unpaired. In few complexes are unpaired. Few paired and was important there, and few unpaired. It could not explain. Example I had given to you. You have to take any metal ion, means one particular metal ion. Number of electrons are same, but sometimes electrons are paired, means complexes are low spin, less magnetic moment, and sometimes electrons are not paired, high spin, more unpaired electrons are there. So when are paired and when not are paired, for that VBT has explanation. What said? If ligand is strong, then there will be the pairing, low spin. If ligand is weak, then there will be the high spin or no pairing. It was explanation. But which ligand is strong and which ligand is weak, it could not explain. So ligand strength, spectrochemical series that is there after the crystal field theory or within crystal field theory, that ligand strength was not explained by VBT. Are you following what I'm saying?
Yes, sir.
Yes, sir.
Such card sheet should be there with you when you study, no, when you see any video or when you read the content. Then such a card sheet, as like on the screen you are finding the 6 points are there. Actually in that one card sheet you can have sessions, limitations of PPT, maybe one particularly or small portion also, only points, and with the help of points you should able to explain, should able to elaborate, then it will prove that you know the things, you know to use your brain to recall. Okay, limitations of BBT, basis of CFT, application of CFT to octahedral complexes, application of CFT to tetrahedral complexes, or say single complexes, various geometries or various coordinate number. So in one card sheet, a playing card remains of that size only. If you consider one page, see, such a page, a small page also can be with what the lot many things, and with the help of that you should only writing has also no meaning, you should able to recall that. Means if I have to say the color, then color is not explained, only one line not sufficient. Example also I do, for example, copper ammonia complex, potassium ferrocyanide complex, many complexes are there, coordination compounds, they are colored, but color of no complex was explained by the VBT. With example you are explaining, that's elaboration. Here see, second point is D2sp3 and sp3d2, that's inner orbital and outer orbital. Crystal Petri was saying inner orbital complexes are more stable, outer orbital complexes are less stable, but within inner orbital complexes, who will be the most stable, who will be the less stable? Cyano complexes you can give example, outer orbital complexes, chloro complexes you can give the example. That comparison was not done. Yes, are you following what I'm saying?
Yes, sir.
Similarly,
Yes.
one more point I explained, say stability. So about means point number 2 and point number 4 are related, but point number 4 emphasizing more clear cut exact idea about the stability, means measurement of the stability. It was relating general comparison, and here particular stability for the complexes as per CFSE concept, how you could able to calculate, you could not able to find that. And when this concept is more clear, if you study CFT, no, then whatever you are studying in CFT, those are the limitations here. In CFT, you are studying 10 DQ value and measurement of 10 DQ or explanation of colors. Yes, that's a limitation. Here you are discussing the spectrochemical series and the strength of the complexes, stability of the complexes, which was not explained. That's a limitation. Here in unit number 2, you are discussing. In CFT, it is not there. In unit number 2, this point is there. Substitution reaction and thermal stability. Actually, we are studying that unit number 2. There, substitution reactions or rate of the reaction, speed of the reaction, or thermodynamic stability. In that topic, if you study that, you will understand that was not explained by VBT. Means whatever advanced study you are doing, because those were not explained by VBT, whatever advanced studies there, those remain a limitation. About stability, CFSC particular calculations you have done, that is a limitation. About the magnetic property with change in temperature, splitting parameter, with the help of that we could able to explain that. Again, it is application of the CFT, the low spin and the high spin complexes, the 10 DQ value. If 10 DQ value or splitting parameter, say delta O, if greater than pairing energy, then low spin complexes. If delta O is less than pairing energy, then high spin complexes. So there you are studying crystal crystallography. Here, if you correlate that, then you will understand, yes, there's a linkage in the study. Or if you remain only at the by-hearting mode, mechanical study mode, it is asked no to remember only. So you will remember, there's no question about that. But only memorization is not the purpose of the study. Then any 5th standard student also can remember. 10th standard pass student also can remember the way with which you are following. And how can we say you are grown up in the study? 10th standard student grasping, understanding will be different than you. And it should be. If it is there, then only you have grown up. Then only you are studying properly. Yes, students, I am not here to demote you, but I want to tell you the reality and how should your approach. How can you not study? Is it clear?
Yes, sir.
Sir.
Yes, sir.
Yes.
Yes, sir.
So let us start now the new topic. As we have already started, no? That point we were discussing. Last time I was discussing metal orbitals. For what? Sigma bonding. And on the board, I represented all the orbitals. If I start from the, say, 3D orbital. Which are the 3D orbitals? Be fast now. Yes, which are the 3D orbitals?
dx square minus y square,
Yes,
dz square,
yes,
dxy,
yes.
dxz,
Okay,
dyz.
okay. Out of these two, sorry, out of these five which are involved in the two sets, one set is axial and one set is non-axial. Which orbitals are axial? My question is, which
D,
orbitals are axial?
D,
dz square
DZ
dx square minus
and
y square.
First two, right? Absolutely. These are axial. And our ligands are approaching along axis. Means if I consider x axis, negative direction of x is positive direction of y, negative direction of y, upside is z, downside is z, and ligands are coming along the axis. So orbitals or the lobes which are along axis, they will experience direct interaction, head-on interaction. So sigma bonding will be there. So out of those five, which are suitable for sigma bonding? Which orbital is suitable for sigma bonding?
dx square minus y square and dz square.
Yes, these two orbitals are suitable for what? The sigma bonding. Now next orbital, say for s. So it is only one. That's a s orbital. Is it suitable for sigma bonding?
Yes.
Yes. Okay.
yes,
Now come to the next 4p, which has px, py, and pz. Are they along axis? Are they suitable?
Yes, sir.
Yes.
So these six orbitals, axial d orbitals, s orbital, px, py, and pz, those can form sigma bond. Those are suitable to form sigma bond. If they are forming bonds, as per molecular orbital theory, if there is a constructive interference, means positive interference, then there will be bonding orbital. Are you following what I'm saying?
Yes, sir.
If there is a destructive interference, negative interference, there will be anti-bonding orbital, high energy orbital. Constructive interference, low energy orbital. Destructive interference, high energy orbital. And if there is a no interaction, two reasons are possible. One reason, there is a no suitable orbital to overlap. No interaction, no overlap at all. No overlap at all. Listen carefully. No overlap, no interaction at all. So zero interaction. And other possibility, one side there is a positive interaction and other side there is a negative interaction in the same interaction. 50% positive, 50% negative. So net interaction will be zero. It doesn't mean no interaction. Interaction is there, but equal positive and equal negative. In such cases also, non-bonding orbitals may possible. But our point of interest here is these orbitals. These are non-axial orbitals. We say them as T2g orbitals. I had told you about the nomenclature of these orbitals. Yes, in last lecture, I had discussed nomenclature, names of the orbitals.
No, sir.
No. Okay. So these are T2g. I explained that point. These are T2g orbitals, non-axial orbitals, which are not suitable. So they will remain non-bonding. No bonding. The energy will remain same. Now let us understand labeling of these orbitals. We are talking about the orbitals on the met line one by one. I'm talking about these two. Now, these two and their labeling. Rule I tell to you. If there is a singlet, only one set, only one orbital, then label is A, small a or capital A. Actually, B also is used, but this time we are not using that. So timing, remember, only A. Actually, A or B is a rule. But timing, understand, single means A. Single means only one orbital. If two are there, yes, will anybody tell me what may be the label? If two are there, then
2A.
no.
EG.
Only E. E means doublet. Now, if three are there, three orbitals are together, then
T. T.
repeat.
T.
Yeah.
T.
Right. T, copy. It's a T. So singlet only one means A, two means E, and three means T. Now let us see. This set, how many are there?
2.
So which symbol will be there?
E.
Yes, E. How many are here?
3.
Yes. Which symbol?
T.
Right.
T,
Right. How many orbitals are here?
1.
Which symbol?
A.
Good.
A,
Now last, all three are there. No, PX, PY, PZ. How many are here?
3.
So which symbol?
T.
Right. Yes. All other students, are you following what we are discussing?
Yes, sir.
yes, sir.
Good. You are brilliant. Now, second rule, pay proper attention. If orbitals are axial, then 1 means along axis. If not, then 2. If along axis, then 1. If not, then 2. Is it clear?
Yes, sir.
Okay, now this set, now I'm asking this one. This set Px, Py, Pz along axis or not?
Along axis.
One or two?
One.
1.
Right, one. S orbital along axis or not? Actually, spherically symmetric, so all round personality it is.
Along axis.
Along X.
Yes.
One or two?
One.
Good, good. Now this orbital dxy, dyj or dxj, this one, these three along axis or not?
Not.
Not. So one or two?
Two.
Right, two. Okay. Now about this, no, actually one could be used there. They're along axis. Here I'm talking about this E. But practically, by practice, this doublet which are there, no, they're along axis. Therefore, we are not mentioning them separately. But if somebody use one there, nothing wrong. So for E only, for dx square minus y square and dz square orbitals, that set, for that set, we are not representing one or two. Simply E. Other where that labels are given. Now I want to discuss the next point. That's gyradness and ungyradness. Have you heard that gyradness and ungyradness? G means gyrade and U means ungyrade. Have you heard?
No, sir.
No. Okay, great. But then for that I give some explanation. Then we'll come to application. G means centrosymmetricity or centrosymmetric. Students could be able to read what I am writing,
Yes,
or is
sir.
it blurred? Clearly readable, no?
Yes.
Yes. Ungyrate means it's a non-centrosymmetric. Now, if I consider, say, S orbital, spherically symmetric, S orbital, and if I represent the wave function, then throughout this orbital, there will be positive wave function. Yes, could you able to read that positive sign or it should be larger? Please reply so that how should I write? I'll come to know, no? That positive sign could you able to read or it is a very small one? Yes,
Small.
small one. It is small. So just wait. I am representing now the S orbital, and within that S orbital there are signs, wave function, positive, positive. Is it readable?
Yes, sir.
Yes, sir.
Throughout that S orbital there is positive sign. Now what I do, I take any point, say this point, draw a line up to center. Here's the center. Extend the line to same extent here. I started from positive section and I'm ending in positive section. Similar point I am getting. So there is center of symmetry, gyradness, S orbital, center of symmetry is there. So center of symmetry, that's the molecular symmetry topic you have studied, no? If there is a center of symmetry, not in the molecular arrangement, from wave function distribution point of view, then it is gyrate. Is that gyrate word clear?
Yes, sir.
Yeah. Now I draw in front of you one shape. It is a dumbbell. Answer for my question. Is there center of symmetry? See, don't go on the just distortion. It's a perfect shape. Yeah. Is there center of symmetry? Only shape, only dumbbell.
Yes, sir.
Good, very good. See, take this point, draw a line up to center and extend the point to extend that line to same extent. A point at periphery, not exactly middle, just down. Here point came up. So similar point you come across. So there is center of symmetry. Center of symmetry, you can say I. But students, we are discussing here the wave function. If it remain positive, then what will be the wave function other side? What will the wave function for this lobe? Negative. Yes. One lobe is positive and other lobe is negative. Now answer for my question. Is there center of symmetry? Means if I start from say this point, draw a line up to center, extend the line to same extent. Yes, I'm getting similar point, but see the wave function. What's the wave function at this point? What's the wave function at this point?
Positive.
Right.
Positive.
And what is the wave function now after inversion?
Negative.
Right. You're positive or you're negative. So can I say there's a center of inversion? Sorry. Can I say there's a centrosymmetricity?
No.
No. So which symbol shall I use?
U.
U. Ungyrate. Is it clear?
Yes, sir.
Now, if you know,
Yes.
if you, yes, somebody said no. Yes, anywhere no. If no is that, I'll repeat. Will you apply this concept now?
Yes, sir.
Okay, apply the concept now here. Tell me for these orbital dx square minus y square and dz square. Gyradness or ungyradness? D orbital.
Gyradness.
Good. Therefore, we represent Eg. So those students who could not able to answer, they have to work on that. They have to work on this point. Which point? Gyradness and ungyradness. They draw the shape of the d orbital and see. Positive will end to positive. Negative will end to negative. Opposite lobes are with. In case of p orbital, case remains different. In case of d orbital, case is different. So label for that orbital or orbitals, those orbitals is Eg. Is this label clear? Eg means dx square minus y square and dz square. Axial orbitals of d set. Is it clear?
Yes, sir.
Okay, now answer this question. dxy, dxj, dyj, these orbitals, these three orbitals. I am talking about these. Gired or ungired?
Gired.
Yes, it is also gired. All d orbitals are gired. T2g is a representation. Is it clear? So Eg is a one set. Set I am saying, which has two orbitals. Which are those? Dx square minus y square and dz square. T2g, three orbitals. Which are those? Dxy, dxz and dyz. Now come to this s orbital. Answer, centrosymmetric or non-centrosymmetric? S spherically symmetric.
Centrosymmetry.
Yes, only one wave function, positive or negative. Positive and negative will not be there in case of S. Either it will be positive or it will be negative. So, what should I write here? G or U?
G.
G.
G. A1G is a representation for S orbital. Now, about these P orbitals, Px, Py and Pz. Are they centrosymmetric?
No.
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 Yes. Already I told you, yes. Which symbol then?
U.
U.
Yes. T1U is a representation for 4P. So in MO treatment, we will use these symbols. We will represent 3D orbital by two sets. One is EG and other is T2G. It is a representation of 3D. If I have to represent 4S, then which symbol? 4S means only one.
A1.
A1
G.
G, right. Now 4P,
T1U.
T1U. So these are the representations. Out of these, only these orbitals EG, A1G and T1U, they could able to form sigma bond. These are the only orbitals who can form sigma bond. How many such orbitals are there? Just count. EG means two orbitals. A1G means one orbital. जस्ट वेट सर लेक्चर चालू आहे घरी घरी आहे सर घरून चालू आहे हा हो येतो हो या भेटतो हो EG A1G and T1U yes E means 2 A means 1 T means 3 yes how many are there total
6.
6.
right these 6 orbitals are suitable to form sigma bonded molecular orbitals. We are talking sigma doesn't mean that in coordinate compound only sigma bonding remains. Pi bonding also remains. We are discussing, but stepwise we are going. So in this last lecture and this lecture, what we have covered, which orbitals are suitable from metal ion to form molecular orbital, sigma molecular orbitals, and labeling of those orbitals that we have covered. So that is the first point in your now this unit number 2. Is that first point discussion clear?
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Now shapes
Yes,
of
sir.
orbitals are represented. Now the second point I want to cover, actually I planned that it should be covered. Shall I go to the next point now?
Yes, sir.
Yes, sir.
Yeah. Now we are talking about the orbitals. Orbitals from ligand and their shapes we have to represent. If you go to the book by seeing the diagram, you may confuse. Simple things are there. No need to worry about that. Yes, do you have those diagrams in front of you now? So it will be easy for me to discuss. Yes or no?
Yes, sir.
Let me see that those means on the internet if I could able to find no clear cut all diagram in your book they are the good. Yes, everybody is with the book now. If it is there, then it will be easy for me to explain. If no, then say no at this moment. Next time you can be with the book so that we can cover the concept some easily. Means what I'm doing, I'm avoiding to draw the all diagrams structure. No, if you remain with, then we cannot discuss. That was my point of interest. Okay, no, it is not very fair diagram. Okay, could you able to see this diagram now? Whatever I am showing, hint I give to you.
Yes, sir.
Yes.
Yeah. This diagram I can't now show. Okay. In this diagram, it is S orbital and our ligands are coming. Let me consider it is a x-axis, it is a y-axis, and upside there is a z-axis. So whatever these here we can say L, ligand you can consider. But from orbital point of view, if we have to show, of course, those ligands they want to what represent, but where there will be interaction, how will the interaction that I want to what show. So I remove this L and in spite of that I represent the wave function. if I consider wave function for s orbital positive and I want there should be constructive interference. Example, two types of interference are there. Two types of interactions are there, additive and subtractive, constructive and destructive. And I want here constructive interference. And for constructive interference, wave function should be same. Combining wave functions should be same. So here s orbital, which is positively charged, means wave function positive. Answer for my question, what should be wave function for ligand? Here, positive or negative?
Positive.
Right, positive. Here,
Positive.
right. Here,
Positive.
right. Here,
Positive.
positive. Everywhere there will be positive. So if you open the book later on, open the book and you'll find such kind of representation. What they did in the book, in spite of showing this circular, they have shown such kind of the lobes. Means here is a one lobe, here is other. Means from upside maybe the one is coming, downside one is there. My drawing is very excellent, no? So I was not intended to draw this. Are you understanding what I am drawing?
Yes, sir.
Or difficult?
Yes, sir.
Okay. So here all were positive, 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 positive functions are. It is our ligand group orbitals. It is not a ligand, one ligand orbital. All ligands have come together and they are establishing one group, ligand symmetry group, and that symmetry orbital. And label for this orbital, separately represented, label for this orbital is same as like the orbital from metal. That's a A1G. So it is a A1G set from ligand. Could you able to understand what I'm saying?
Yes, sir.
Okay. Now, one more example I discuss with you. See, I'm talking about this orbital. Will anybody tell me which Maitland orbital is this one?
dz square.
Right, dz square. Understand that orbital first. Here, there is a positive sign. Here, the duff is there, no? Here, duff. Could you able to see that? There's a negative wave function. And at bottom, there's a positive. Yes, could you able to see what I am showing or difficult?
Yes, sir.
I think you could able to see now because I magnified that. Could you able to understand?
Yes, sir.
Yes, sir.
Yes. So here there is a positive. Upside there is a positive sign. Middle duck portion is there, here negative sign, and downside there is a positive sign. It is our dz square orbital. And for the sake of convenience, for the sake of explanation, I want constructive interference there, additive interference. So wave functions should be same. So if it is a positive, then what should be the wave function here for this S? Positive or negative?
Positive.
Right. So here positive. What should be the wave function for this? Positive or negative?
Positive.
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 Therefore, those are shown by white color. Those lobes, that portion is shown by white color. Wave function should match. And now here negative section is there. Negative region is there. This region is negative. This is interacting with this, and this set of the orbitals. If it is negative, then what should the wave function for this?
Negative.
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 What should the wave function for this?
Negative.
Negative. What should the wave function for this? Negative. What should the wave function for this? Negative. So in your book, they have shown separate orbitals. So they have shown here it is actually only one orbital. What is that orbital? It is you will label me, you will tell me which set is there or related to that orbital. This one and other one. Combining that, there will be the EG set. This is one where wave function is positive, and from bottom side there will be the one here wave function is positive, and from along x-axis positive direction there is one which is negative. From negative x-axis direction there is one which is negative. From positive y-axis you can consider there is one negative. From negative y there is one which is negative. So what is this? It is a ligand group orbital, LGO or LSO. It is in the category, means it is for what? To interact with dz square orbital. So this is a one orbital and one more orbital is there. It can be combined and it is represented as EG. So EG is a set. Out of that, only one orbital is represented here from the ligand. Now what about the second orbital? Yes, could you able to understand what I'm saying?
Yes, sir.
Now what about second orbital? This one. Here is the second orbital hidden. What are we finding? Here negative wave function. Here negative wave function. Here positive wave function. Positive wave function. So related to that, where your ligand group orbital will be there. So this orbital and this orbital, those will combine, and that will be our EG set. EG set from the ligand. Symmetry should be same. is the essential condition to form the molecular orbitals. So that we are what following. If Eg set is there from metal ion, then Eg set should be there from ligand. Then only there will be the molecular orbital formation. And we are talking about the sigma bonding. So for sigma bonding, Eg set on ligand also remain and they do overlap. But Eg set, T2g set, T1u set will be the confusion. So separately for orbitals, these diagrams are represented. So whatever I represented here separate for the ligand, this is the for the dz square orbital combination. It is from the ligand which can combine with dz square orbital. But labeling for that set will be Eg, T2g, T1u or A1g as is there in the metal ion, and those suitable symmetry orbitals will combine to produce molecular orbitals. So you do one thing, you can go through the book. If problems are there, next time we will have the further discussion. What you have to do, go through the book and you have to represent all the orbitals from ligand. Orbitals from metal ion I already discussed, as like I represented here the orbital from ligand. See, it is orbital from ligand related to combination with 4s. This orbital from ligand related to combination with dz square. Similarly, you have to represent the orbitals from the ligand which are suitable to combine with particular orbital. Here only one type of constructive interference we are considering, so accordingly represent. So how the orbitals are there, symmetry orbitals are there, what are their wave function, that concept will be clear. Is it possible?
Yes, sir.
Yes, sir.
No, somebody said no, likewise I heard. So if you have no book as such, no, then somebody will the book, take the snapshot of that and you can circulate that. I think it is easy, it is convenient, you can do. Am I right?
Yes.
Yes.
Okay, amongst you have the circulation and you can complete that. So we have covered orbitals of metal ion and we have covered orbitals from ligand. Then we have to set the molecular orbitals, molecular orbital diagram. So next time we will set the MO diagram. So while preparing the notes, see previous 30 lectures are there, no, I think 30 lectures, yeah. Notes you have to upload. I hope that you are prepared. Videos were given to you. It's a bit natural. You have to compare the notes. Within 2 days, I will give the assignments and you have to complete those assignments. How much time you want to complete those assignments? Up to end of this month possible? Because like videos you told, no, videos you have seen, you have studied, so it is expected you should draw the notes. Yes, Roshan, is it possible up to end of this month?
Yes, sir.
Muskan,
Yes, sir.
Alia,
Yes, sir.
Rushikesh,
Yes, sir.
Vaishnavi.
Yes, sir.
Yes, Shruti has already answered. Rupashri,
Yes, sir.
Swapnali, no, I could not hear you, Swapnali. Chetan,
Yes, sir.
okay, Swapnali network issue may be there. Okay, students, so shall we stop now?
Yes, sir.
Okay, I'll stop the recording in case if questions are there. Next time we'll have the discussion, and remember follow-up sessions are going on. So you have to read the topic crystal field theory. Next time I will ask the revision.